In my last video the other day, I worked out example 11.5 using energy initial equals energy final. And the energies were thermal energy, and it was thermal energy with a reference where the 0 point was water, liquid water at 0 degrees Celsius. So to figure out what that initial energy was, I took the MC, the mass times specific heat times temperature of the ice, which is going to be a negative value, the mass times the latent heat of fusion of the ice, and that is going to be just multiplied by -1 because that's all you have there. There's no change in temperature. And then the mass times specific heat of water times its temperature. And that will give you the total heat in the system. And when I say the total heat, I mean relative to liquid water at 0 degrees Celsius. Now notice that is different from what they did in the text. They have the heat of the ice plus the heat of the melting plus the heat of the ice water plus the heat of the water equals 0. Oh, I should finish off this side on the right before I make this full comparison. I said on the right hand side we got the mass of the ice plus the mass of the water times the specific heat of water times delta T, which T will be, I guess I'll just write T because it's T in Celsius. That is assuming that all of the ice melts and converts to water. On the other hand, if it doesn't melt, then we'll be looking at however much ice is the mass of water that stayed ice or becomes ice times the latent heat of fusion of ice. And with that, we would be finding how much we take the energy over here, which is a negative value, and compare it, and you'd end up with how much, and if it came out to be, if energy is less than 0, then you'd get this, and you can find out how much mass stayed ice, and then this would be at 0 degrees Celsius. If the mass, though, turned out to be greater than mass of ice plus mass of water, you'd still have another level, which would be Mi plus M water L sub F, and that would be negative, minus the mass of, it'd be the total mass again, M ice plus mass of water times the specific heat of ice times your temperature, and that temperature is going to be a negative value. So this would be the amount it would take to freeze all of the water and the ice, and also bring the all of the water and the ice down by a certain amount of temperature. So this is kind of a so there's 3 conditions here. If E is greater than 0, you end up with a final state of just water. If E is less than 0, generally you're just going to have a certain amount of ice left and everything will be at 0 degrees. And this one is E is much, much less than 0, so that the mass of the ice is greater than the total amount of mass that was there. But what I'm going to find in exercise 11.5, it's a little different from the example, because instead of solving for the final temperature, we're going to be solving for the mass of the ice. And so in this one, instead of using the initial energy, the total initial energy of everything equals the total final energy of everything, I'm going to be using the heat added to the ice equals negative of the heat added to the water. And the reason I'm doing it this way is because this way the mass of the ice is constrained to one side, because m is what we're going to be solving for, and everything else is on the other side. Everything related to the water. Everything related to the water is known. In fact, the right-hand side, I'll write it over here. Okay, the right-hand side is negative mc delta T, which is going to be the mass is density times volume times specific heat times delta T. What I they will are they going to use salt water to put a whale in? Probably so. So I'll say 1025 for the density of salt water times the volume of 1200 cubic meters times the specific heat of water 4186, and then negative delta T. We're going from 20 to 10, so negative delta T is 10 degrees Celsius. So this is the amount of energy that the ice is going to gain, and it's going to be equal to 51.5 times 10 to the 9th joules, or 51.5 gigajoules. On the other side, we're going to have all of these things happening to the ice, but it's going to be the same mass throughout the time. It's going to have a specific heat of ice going up by 10 degrees from negative 10 to 0. And then it's going to have the latent heat of fusion. So it's not changing any temperature there. So it's just mass times the latent heat of fusion, and I multiply it by 1. And then the mass times the specific heat of water times 10 degrees, which means that it's going to be going up according to the specific heat of water. So now by multiplying the specific heat of ice times the change in temperature plus the latent heat of ice times that, and then specific heat of water times its change in temperature, and then multiplying by the original mass of the ice, we find that all these things together come out to be 395,760, and our final calculation turns out to be just a division. We just take this number and divide by this number and get that number. So now let's go ahead and look at example 11.6. We have a 5 kilogram block of ice. Let me actually write this as mass of ice at 0 degrees Celsius. So if I'm going to choose right now, we are looking for the mass of the ice that was melted. So we could really do this with either of the two formulas. Nothing's preventing us from doing either one. However, there's a little hint here. Based on find the final temperature, neglecting the heat capacity of the container, and find the mass of the ice that was melted. Part B makes it sound like not all of the ice was melted. So if we do part B with the heat, this suggests if we assume the final temperature is 0, which is, it's dangerous to make assumptions like that. Q ice equals Q water. this one is initial and this one's final. But this one's Q ice and Q water. Okay, so the water is MC delta T, and this should be negative. And it goes 10 kilograms of water times 4,186 times a delta T of final minus initial is 0 minus 15, but we're going to make that negative, so it'll be 15 equals, comes out to be 627,900 joules. So this is the amount of heat the water lost, assuming that it goes all the way down to 0 degrees. All right, so on the other side, we'll just put mass of the ice times L sub F. Because it started at 0 degrees Celsius, there's no MC delta T term, so it's just going to gain energy according to this. So if this mass turns out to be less than the original mass of the ice, then this will be okay. 927,000. And let's write down the domain for this, okay. Assuming 0 is less than m is less than 5. If this doesn't come out to be true, then this is going to be wrong. So L sub F is 333,000. So we do that calculation. It looks like it's going to come out to be about 2. Came out to be 1.88 kilograms. And the temperature of the whole system is going to be 0. It's going to come out to an equilibrium temperature of 0 degrees Celsius. If I did it with the E initial equals E final, I could have used this formula, mass times specific heat of the ice times its temperature, but its temperature would have been 0, so that would have come to be 0, plus mass times the L sub F times -1, and then the mass times the specific heat of the water was 20. And then look over here, it would have come out to be a negative value if I had done this. And since it came out to be a negative value, I wouldn't use this equation to find the final temperature. I would have used this equation. And then since the mass came out to be the mass came out to be above or less than the total mass of the system, we didn't have to worry about freezing the whole thing. So question 11.6 asks, what effect would doubling the initial amount of liquid water have on the amount of ice melted? And since the amount of ice melted was 1.89 kilograms and the amount present at the beginning was 5 kilograms, we can say that the amount of ice melted here is probably going to be double the amount. If because you got basically double the heat from double the water. If let's say there had only been 3 kilograms of ice present, though, there would have been a different effect. You would double the amount of liquid water brought down, but you'd end up having them meet somewhere in between with the final temperature. I think, though, now that I'm looking at it, I think this equation with its all its conditionality is more robust than working with the changes in heat, or the heats of the ice equal negative heat of the water. Energy initial equals energy final. Though this over here looks really, really complicated, this is a little bit more robust of a version because we can calculate the initial energy, and then if that initial energy is above 0, and we can say everything ends up as water at some final temperature. If it ends up less than 0, then we end up with a delta M, the amount of water that has converted to ice, times latent heat of fusion of the ice. And actually, I guess I should make that negative. Since this was negative, this would be negative as well. And then if that amount of ice that was frozen ends up being greater than the mass of the water plus the mass of the ice, then your final energy is going to equal this, which is actually going to be a constant. And then you can calculate the final temperature of the ice using this equation here. So let's do exercise 11.6 using that formula. We've got 8 kilograms of ice at minus 5 degrees Celsius. So that means we've got 8 kilograms. Ice has specific heat of 2090 and it's 5 degrees Celsius. We're going to go ahead and treat the initial energy as though we are freezing it all. So that is, actually, I guess this should be a negative value. So that same 8 kilograms times 333,000. I'll just put a -1 there. And it's added to 12 kilograms of water at 20 degrees Celsius. So we're going to have that 12 kilograms at 20 degrees. And it's, to heat it from 0 to 20, you would need 4,186 joules per kilogram per degree Celsius. So that is your initial heat in the system. Heat measured from the unfrozen state of water. And it comes out to be negative 1.74 times 10 to the 6th joules. So since that came out to be negative, first we're going to try this value, equals negative delta M times the latent heat of fusion, 333,000. And it comes out to be delta M is 5.23 kilograms. Now we started with 8 kilograms of ice, and we ended with 5.23 kilograms, which means that actually 2.77 kilograms melted. If this had come out to be a much, much larger magnitude number, it would have turned out that some of the water actually froze. Because this number could have been anywhere between 0 and 20, because 8 plus 12 is 20. And if you had gotten like 19, it would have meant that a considerable amount of the water had frozen. But if this number had turned out to be 21 or had turned out to be greater than 20, then we'd have to consider the final temperature of the ice.